Swayam Prabha. Digital India. Educated India.
So, hello everyone. So, we'll continue with the numerical part of evenness, and in last class we are discussing the limit irregularity, how to calculate the limit irregularity. So, we have seen that with this relationship where the factor is constant is 110 for any fiber, like say for a particular type of cotton we have got 110 by under root any. We have seen the variability has increased from 35% to 45%. Now, the next numerical is that with average 120 fibers are there in the yarn cross section. So, this is for wool as well as the cotton. So, we have produced one yarn, wool and a cotton. So, the average number of fibers in both the cases 120 such fibers are there, 120. Now we have to calculate the limit irregularity. So we know the relationship for wool limit irregularity, wool 112 by under root n number of fibers. For cotton 106 by under root n. So here it will be 112 by under root 125. Here 106 by under root 125. So this is in percent. Okay. So we can calculate in this fashion the limit irregularity for wool and for cotton. So you see that this has become 10.6 for wool and 9.68 for cotton. Now here if we use finer wool fiber, okay, for same yarn linear density, the number will be increased. So accordingly the limit irregularity will reduce. Now let us try to do another numerical. If the most uniform 30 text polyester staple fiber yarn has CB of 15%. Now here the term most uniform means the spinning system is running perfectly. So that means we cannot produce a yarn from 30 texts for 30 texts yarn less than 15%. So in that case, so the lowest CB, so less than 15%, lowest CB for CV limit for 30 text yarn is 15%. Okay. Now what we want to do, we want to calculate the CV limit for 10 ticks yarn. This is the condition from same fiber and the same spinning system. That means spinning system means it's a running perfectly. There is no problem. That's why it's producing the lowest yarn CV. And same fiber means fiber linear density will be same. So from this to what our approach is that, so we know the limit CV and polyester is given, so that means the limit CV formula will be 100 by under root n. Now n is the number of fibers. So first condition, this is condition 1 and then the condition 2. With the condition 1, this limit CV is, it is 15. So let us calculate the number of fibers for 30 ticks. Number of fiber in 30 ticks. So under root n will be 100 by under root 30 ticks. 30 ticks by 15. So n for in 30 ticks will be 100 by 15 square. It will become 44.44 number of fibers. And we know the 30 ticks yarn. So per fiber the ticks will be, so now ticks of fiber will be 30 by 44.44, 0.67. This is the ticks of fiber. So if we calculate the ticks of fiber, so the same fiber is being used. So for 10 ticks, so now condition 2, for 10 ticks yarn, so number of fiber in 10 ticks will become yarn ticks. Yarn ticks, which is 10 by 0.6167, it will become 14.9. So typically approximately 15 fibers will be there in the yarn cross section. So now we can calculate the limit irregularity. V limit 15, 100 by under root 14.92, it will become 25.88. So we can see when we produce coarser yarn from same fiber, the limit irregularity is lower, and from the same fiber if we try to produce the yarn, finer yarn, the limit irregularity increases. This is mainly due to number of fibers in the cross section. So if we reduce the number of fiber in the cross section, then we will result a uneven yarn. So this is calculated here. You can see it is becoming 25.98, that we have already discussed. Next, Here we are trying to compare the performance of two ring frames. Now try to see, ring frame 1 is producing 25 tex polyester yarn with CV% of 9%. That means it's CV. So ring frame 1, first let us see ring frame 1, and here it will be ring frame 2. First, with ring frame 1, the fiber denier is 1.5. So 1 fiber denier equal to 1.5. So if we can convert it to tex, so 1.5 divided by 9, it will become, that we can calculate it, 1.5.166 tex. This much tex. Okay. Now for 25%, 25 tex, the number of fibers, yarn 1 will be 25 divided by 0.166. Yarn tex by fiber tex 150.6. Okay, and here you can see that ring frame 2 is producing higher, the ring frame 1 is producing higher unevenness. Okay, now let us calculate the limit irregularity. V limit, as it is polyester fiber, it will be 100 by under root 150.6. Limit irregularity for 1, 8.1. This we can calculate, it's 8.14, and our irregularity is given, so we can calculate the index of irregularity I for first ring frame. So actual irregularity 9 divided by 8.14, it will become 1.1. Okay, now for ring frame 2, similarly V limit 2 we have to calculate. So denier of fiber become, in place of 1.5, now we have changed the denier fiber 1, and tex will be 1 by 9.11 on tex, and number of fibers in the cross section of yarn from second ring frame, it's again producing 25 tex. 25 divided by 0.111, 27.227. So number of fiber has increased from 150 to 227. This is mainly due to the reduction in fiber depth. So as it is, number of fibers have increased, so limit irregularity will be 100 by under root 227.27, it will be 6.65, 6.63. So this value will become 6.63. Now if we calculate the index of irregularity of ring frame 2, it will become 8.5 divided by 6.63. It will become 1.28. Now to judge the performance, we have to compare the index of irregularity. So as index of irregularity of ring frame 1 is lower than ring frame 2, so lower the index of irregularity, better will be the performance. So performance is better in case of ring frame 1, although ring frame 1 is producing higher CV% than ring frame 2. So final CV% is not the indication of running performance of a ring frame. This is final CV% is product related performance, but machine performance is based on the index of irregularity. Now this is only possible by changing the fiber density. So if we use the finer fiber and we are getting little bit better CV%, that doesn't mean that the ring frame is running better. Now this is the solution is here given. Number of fibers in the yarn cross section approximately. So limit irregularity was 8.16 and index of irregularity 1.1, and ring frame 2 the number of fibers was typically 2.27, 1.28. So the higher index of irregularity value in ring frame 2 indicates the poor running performance. So these two things are separate. Yarn ring frame 1 is producing higher CV% and ring frame 2 is producing lower than that. It doesn't mean that ring frame 1 is always producing better, having better performance. Okay. Next, if the most uniform 20 tex polyester staple fiber yarn has CV% of 16, what is the lowest CV of 8 tex yarn produced from the same fiber? Now, and what would be the CV% of 4 ply yarn made from 8 tex yarn? The similar steps will be there. Yarn count is given 20 tex and limiting is a most uniform yarn, that means limiting CV is 16%. As the most uniform yarn is mentioned, so when most uniform yarns will be mentioned, that is the maximum, that is better, most optimum performance of machine. So this is limiting irregularity. From there we can calculate the number of fibers. So number of fibers is N1, and from this relationship we can calculate the number of fibers here. Number of fibers at 39.06. So 39 approximately number of fibers are there. From there we can calculate the takes of fiber. So 20 takes is the yarn takes. So takes, fiber takes is 20 by number of fiber. So what will be the takes here? Takes is 0.51. So that's the takes of fiber. So if we get the takes of fiber and same fiber is being used, so for 8 takes yarn we can calculate the number of fibers. So number of fibers will be 8 by 0.512. So number of fibers here 8 by 0.512, it's 15.62. So here 15.62 we have got number of fiber. So limit irregularity we can use V limit 100 by under root 15.62. This is a limit irregularity of 8 takes here. So 100 by under root 15.62, it's 25.3. So that is a minimum irregularity or minimum CV possible for 8 takes yarn is 25. So for 20 takes coarser yarn it was 16, and if we make it the finer yarn, so number of fibers has reduced, so irregularity has increased. Now next is what would be the CV% of 4-ply yarn produced from 8 takes. So 4-ply yarn, this part we will discuss later also in detail. So if we make it ply, so the CV% further reduces. So 8 takes yarn, so the relationship is that CV% of plied yarn equal to CV% of individual component divided by number of ply. So 25 is the limiting CV. So it's, or 25% of the CV is the CV which the machine is producing. So 25.3 divided by number of ply is 4. So it will become 12.6. So it is coming 12.6. Next numerical is, if the lowest possible CV% of 20 NE 100% polyester yarn is 12%, then the lowest possible CV% of 4-ply 10 takes yarn produced from same fiber in the same spinning line. The similar type of numerical. Now let us try to see. 12% is CV limit. So first let us calculate the tax value. Tax of yarn. Relationship, as we know, 590.5 divided by 20. 29.5. Okay, approximately this is the value, 29.5. 29.5. So this is the tax of yarn. Now let us try to see the CV limit. CV limit is 12%, 100 by under root n, and n for say 20 any. So n will be 100 by 12 square. It will become 69.44. Okay, 69.44 fibers are there, and the tax of yarn is 29.52 tax. Tax of fiber, individual fiber, will be 29.52 divided by 69.44, 0.425 tax. So this same fiber is being used to produce 10 tax yarn. Now condition 2. So for 10 tax yarn, number of fiber in 10 tax, 10 by 0.425, it will become 23.5 tax, 23.5 number of fibers. And now limiting CV, so lowest CV possible. So CV limit for 10 tax will be 100 by under root 23.5. This value 20.61. That is the CV limit. Now we are plying with a 4 ply. So CV of 4 ply 10 tax yarn, four ply of 10 tax yarn would be 20.61 divided by under root 4, 10.30, approximately 10. So in this way we can calculate. So we see the steps here. $69.44, 23.52 for 10 tax yarn. You can see here 20.61 limiting CV of 10 tax, and then we are trying to ply. So 23.52 was the number of fiber we have calculated in the 10 tax yarn. So for 4 ply, this under root 4, that we will discuss. So how to reduce the So CV percent is reduced by doubling. So here 4 doubling is 4, and CV percent of any fiber strand increases by stretching. That we will discuss. So addition and reduction, that we will discuss. So 10.3 CV percent of ply. Next, if the most uniform 40 takes 40 NE 100% polyester staple fiber has 15% CV, then lowest CV of 3 ply 330s NE. So 3 ply of 30s yarn. So similar way we can calculate. Okay. First it will be better to convert the English count to text. So that will be better because directly we can divide. So CV limit is given here, and this is the text. So from there, as it is polyester, we can calculate the number of fibers. CV limit equal to 1500 by under root in 40 NE. So in 40 NE will be 100 by 15 squared. So this will become 44.44. So you can see here. So 44.44 number of fibers. Okay. And this number of fiber are in the cross section of 14.76 texts. 14.76 we have got the yarn text. So text of fiber will be the text of yarn 14.76 divided by total number of fibers 44.4. So that we can get 0.332 texts. Now in the second condition, single yarn count is 30 English count. So 590.5 divided by 30, we get 19.68 texts. And number of fibers in the cross section of yarn 2, that is 19.68 texts. So fiber text we have calculated 0.332. Earlier same fiber is being used. So number of fibers in the yarn cross section is 59.27. Now CV limit we have to calculate for 30 NE, that is 19.68 texts. So it will be 100 by under root 59.27. So that way we can calculate CV limit. 100 by 59.27, it is 12.98%. Now the question is that we have to calculate the CV of 3 by 30s. 3 by 30s, that means, so we have to ply. So the CV of plied yarn will become 12.98 divided by under root 3. It is CV of plied yarn. So what we will get? The value of CV of plied yarn is 7.49%. Okay. This is the minimum CV of 30 any yarn. 3 ply of 30 any. Next numerical. CV limit of mass per unit length of fiber strand, and N is the average number of fibers in the yarn cross section. The relationship between CV limit and N is given by 110. And what will be the fiber length, mass per unit length variation? This same numerical we have done for cotton. Okay, so the value was 45.85. Now, next numerical is that a 40 tex yarn with CV% of 10 is produced from 3 decitex pipe. Okay, so 40 tex yarn, the yarn CV% of yarn 10. Fiber decitex is fiber 3 decitex. That means it will be 0.3 tex. Fiber tex is 3. So number of fibers in the yarn cross section is for yarn tex by fiber tex. It will become 133.33. So the number of fibers in the yarn cross section is 133.33. Now CV limit we can calculate using the formula for man-made fiber, 100 by 133.33. So it will become 8.66. So this is 8.66. Then we have to calculate the index of irregularity. Index of irregularity is the ratio of CV actual by CV limit. So 10 is the actual CV and the limiting CV is 8.66 that we have calculated already. It will become 1.1. So from there we can actually guess the performance of the machine. Okay. So this is calculated. You can see here actual CV limit, actual CV actual by CV limit is the index of irregularity. Actual CV is given, fiber decitex to fiber tex is calculated, and number of fibers was 133 as we have seen. CV limit was there, and it is the index of irregularity is calculated to be 1.15 that we have seen. Now next numerical is a 40 tex yarn with CV of 10% is produced from 1.5 decitex. So index of irregularity, similar numerical, where earlier case you can see here this yarn was produced from 3 decitex. 40 tex yarn, same yarn producing same CU%. Only thing, the fiber decitex has changed. Earlier it was 3 decitex, now it is 1.5 decitex. So 1.5 decitex equal to 0.15 tex. Now number of fibers in the cross section will be doubled here, 40 tex. Number of fiber will be 40 by 0.15, so it has doubled to 66.66. Earlier it was 133.33. Now CV limit will be 100 by under root 266.66. So it will be reduced 6.1. So it is reduced, and we can calculate the index of irregularity 10 by 6.12, which is showing 10 by 6.12, 1.63. In earlier case we have seen the index of irregularity was 1.15 for the same yarn when we producing the same yarn CB but with a finer fiber. That means running performance of the machine is deteriorated. So this will give idea about the running performance 266. So CB limit is calculated and index of irregularity is 1.63. Next, a 50 tex yarn with a CU% of 10 is produced from 3 decitex polyester fiber. So here the difference here, earlier it was 40 tex, now we are producing coarser yarn. Coarser yarn in the machine and producing the same level of CB, and we are reducing the same earlier fiber 3 decitex. So definitely here for coarser fiber, coarser yarn from same fiber we are producing and same CB% we are achieving. That means the ring frame is performing inferior. The poor performance will be there. Earlier it was 1.15 for the same condition with a 40 tex. So let us see, earlier with 40 tex the result was 1.15. Now let us see the comparison. The CB limit here we have to calculate. So 3 decitex means 0.3 tex. So number of fiber in the cross section will be 50 by 0.3. 50 by 0.3 will be 166.66. Okay, 166. 166.66. So CB limit will be 100 by under root 166.66 it will become 7.74. So 7.74 is the CV limit, and we are producing the CV of 10. So the ratio index of irregularity will be 10 by 7.74. It will be definitely more than 1.15. What is the value here? 1.29. So the machine performance is inferior. It's poor performance of this present machine than earlier. You can see here it's 1.29. Number of fibers, CV limit, the number of fibers 1, and the ratio. Now a ring frame is producing 25 ticks of yarn from 2 denier polyester. If the standard deviation of yarn linear density is 3 ticks, so standard deviation is given, the index of irregularity applied. So 2 denier fiber ticks will be 2 denier divided by 9. It will become 0.22 ticks. So number of fibers in the cross section is 25 divided by 0.22. It will become 112.5. Now we have to calculate CV actual. What is the CV actual percent? We have got the CV standard. In place of CV percent, the standard deviation is given. Text 3.0 takes the standard deviation of linear density. So what is the mean linear density? 25 takes. So standard deviation by mean equal to CV. So CV percent what we are producing is the standard deviation is 3 by multiplied by 100, 3 by 25 multiplied by 100 will become 12%. 12% is the CV. Okay, its actual CV is 12%. And CV limit, so number of fibers we have calculated, CV limit 100 by under root 112.5, 9.42%. So CV actual we have got and CV limit. So index of irregularity will be actual CV divided by 9.42. 1.27 is the required answer. Okay, so you can see here the actual solution here. So these are the steps. So actual CV we can calculate from the standard deviation. So number of fibers we have calculated from denier and the yarn takes the limit irregularity is calculated and the ratio of these two. Okay, 1.27. 1.27 is the answer. Next numerical will be done by after some basic concept. So during process of spinning, we gradually stretch the fiber strand, like from sliver to roving, roving to yarn. Every stage we stretch the material. So during stretching, the fiber strand, fibers are moving in random fashion. So every stage of process adds the irregularity in the with the previous stage, because we are handling the staple fiber and that too with a negative way, no positive control over the fiber as we have discussed. So in every stage we keep on adding the irregularity in the fiber strand. So for that we need to calculate the amount of irregularity added. So in the equation of limit irregularity, we have seen that the addition is not like normal addition, like CV% of a strand, say roving, so sliver, CV% of sliver is say X, and during the process of spinning, so in the sliver, when sliver is placed in the roving frame, this is actually stretched and to form roving, and during the stretching process in the roving frame, it is adding one CV. This is CV, sliver CV. This is addition CV. And during this process, when it's adding CV, so the resultant CV of roving will be Z. The CV of roving is Z. CV added Y. So is it the fact that Z we get by adding these two parameters, so X plus Y? No. We cannot add the CV by simply adding X plus Y. From earlier relationship we have seen of limit irregularity, the irregularities are added in the square form. And square of CV. So this square of coefficient of variation, the square of coefficient of variation is added. So this square of coefficient of variation is called as relative variance, or it's a simply we can call it as variance, but actual variance is square of standard deviation. Here in our reference we will call CV percent square as variance. So by using the square of coefficient of variation, it becomes possible to add or subtract the irregularities. So irregularities are added by squaring the CV and then simply add. And then we can get the addition or final products CV. Like on a roving we are taking, and roving is stretched in the ring frame, and we get yarn. If roving has got X CV and Y CV is added to the during the ring frame, so yarn CV will be CV of yarn will be Z. So the relationship is Z square equal to X square plus Y square. So that is the relationship. So Z we can calculate by under root X square plus Y square. Similarly, we can subtract also. Suppose CV percent of sliver is V1 and it's fed to a machine which adds V2. So during the process, as I have given already example, so this is the process. Input CV of the input material, and added CV is V2, V1 is the input CV, and output material has got CV V. So for any machine in the during the spinning, this is the same process we will follow, and thus using the square of the coefficient we can calculate the CV of the output material, or CV of, say, CV of input material is given and CV of output material is measured. So CV addition we can calculate as under root V square minus V1 square. So this V will always be more than V1. So output CV is always more than input CV because CV is added during the process. This may be carding, maybe draw frame, speed frame, ring frame, everywhere we add the CV during drafting. In draw frame, in addition to the drafting, another thing happens where CB reduces. So that is reduction of irregularity, and that is done by only by doubling. The process where doubling takes place is that results the reduction in irregularity. For example, in draw frame, where number of slivers, cut slivers are fed at the back side of the draw frame, and which results reduction in CB. Similarly, in gyro spinning, two strands of rovings are doubled at the back of the back roller, and which results reduction in CB. And in rotor spinning also, it's called back doubling. At the rotor groove, back doubling and rotor groove results the improvement in CB percent. So one of the main objectives of doubling is to reduce the irregularity. So n strands of the materials are doubled. Suppose in draw frame we have n number of strands of slivers are fed at the back of the draw. Okay, and each of having CB of VI. So VI is the individual C, and number of slivers are N. So the output CV without, it's not, we cannot say it's output. So if we say the at the back zone, suppose this is one sliver has got CV of VI. So if we double, say if we mix n number of sliver, n number of slivers, this thick material will have CV of n. We should not call it as output CV. This is the V fed material, VF. That is the CV of that. Here in the machine, if there is no draft, nothing is added, so the same material is coming out. So no drafting is taking place. So in that case, only the CV of double strand will be CV of individual strand divided by under root n. So these are the processes where we can reduce the CV, like in draw frame, in gyro spinning, in open-end spinning, rotor spinning, we can reduce the CV of the fiber strand. Now let us try one numerical related to this. This is related to spinning. Two rovings with CV% of 6% each are fed into the spinning zone. So spinning zone. So this is the one roving. This is another roving. And what we are doing? We are feeding in the ring frame. Okay. And in the ring frame, so let me draw once again two rovings. And then it's drafted. Okay. So this roving has got 6. This roving has got 6%, CV%. And what will be the CV% of the feed material, doubled material? So CV doubled material is equal to 6 by under root 2, because 2 strands are there. So it will become 4.24. So 4.24% is the CV of the input material, total CV of input material. Now this is drafted in the ring frame, and which adds the CV by 6% again. Okay, that is CV added, and CV output material is required. So CV output will be under root of CV doubled V doubled square plus V added square. So it will become 4.24 square plus 6 square. So this way we can calculate the CV% of the output material. Now let us output yarn. So 6% is the coefficient of variation of individual roving. Then when it is fed, 4.24, 6 by under root 2, then added 6%. So it will become, the value will be 7.3. So you will get 7.35%. So in this situation, what we have got? We have got reduction in CV and as well as the addition of CV, but they are in different stages. So reduction and addition doesn't take place in a single stage. Although this is a single process, in that case we have to break the stages. The stages where the stage, particularly the step where the CV is reduced and then CV is added. In this way we have to calculate the CV of the output material. So if CV of the output material is known, we can calculate that how much CV is being added. So next numerical is that 8 ends of slivers, each having CV% of 5%, are doubled and drawn to produce a resultant sliver of the same height. That means at the back we are feeding 1, 2, 3, 4, 5, 6, 7, 8 such slivers. Okay, 8 slivers, and sliver hank or sliver linear density is say S. And what we are doing, we are getting the linear density, same linear density. That means 8 slivers are fed, we are giving 8 draft approximately, because assuming there is no fiber loss. And here it is given the drop frame introduces the irregularity by, so V added irregularity is 2.12%. CV added. Okay. Now individual CV is 5%. Each sliver of 5%. So first we have to calculate the input material. So V input material will be 5 by, as 8 doublings are there, under root 8. 1.76. This is the V. No, sorry, V individual was then. This will be V feed material. V individual was 5. This is feed material of 8 sliver, 1.76, and from there we can calculate the output material. Here added is 2.12%. So output material V output material will be V feed material. So here one thing we should be careful, in feed material we should not take 5 as a feed material. See, we have to take the mass of double mass. So 1.76 square plus 5 square. No, sorry, 2. Plus 2.12 square. It will become 2.75. So 2.75 is the CV% of output cell. So here one thing is interesting, 5% is the CV of input sliver, and output sliver we have got which is improved one. So it has reduced to 2.75. So that means here the effect of the doubling is dominating over the addition part. So this in normal draw frame, although we are getting the same hang, same linear density you are getting, but we are getting improvement in uniformity. So that's the basic function of important function of draw frame, to reduce the unevenness in the sliver. So one of the important function. So you can see here this has become 2.75%. So we will continue with this discussion on numerical on evenness, and we'll stop for now. Okay, we'll meet in the next session. Till then, thank you.